So the first topic is linear algebra. All right, I'll turn off my video for a while so that the whole focus will be on the what I'm sharing on the screen. So linear algebra. Now, why this linear algebra is given so much importance, and what is this linear algebra? Okay, so linear algebra has to deal with the study of linear equations. It is basically linear algebra deals with the methods of solving linear equations. All right, now linear equations, as we know, are you know of this type. um, Say simple a1x plus b1y plus c1z is equal to d1, a2x plus b2y plus c2z is equal to d2, a3x plus b3y plus c3z is equal to d3. So this we know is one of the simplest forms of linear equations, and then we need to solve for x, y, and z. All right, we solve like this. This is linear equations. Now, how do we use this in engineering? Our most of the engineering problems, when other than the simple ones, the complex engineering problems has to go for numerical methods of analysis. All right, and numerical methods of analysis, and in those numerical methods and analysis, you have to deal with matrices and linear equations. Very interestingly, even your differential equation, your partial differential equation, for example, suppose you have a partial differential equation, okay, of some function, all right, like this. Now, both for linear differential equation and partial differential equations, the way to solve in a real life situation is to convert this by approximations to this form, to linear equations form. All right, and then you solve the problem. So when I was studying matrices when I was young, in you know in high school, I used to wonder why matrices we have to study. What is this? Generally we do addition and multiplication of numbers, but why is that matrix multiplication is defined in a strange way? I never meaning I used to wonder, but I didn't understand what it is. Okay, so this matrix multiplication we know is 2 into 2 4 plus 3 7, and this is 0 into 0 plus 6 6. So we multiply the row with the column elements. So I wondered why this is so, and the answer lies later is in solving differential equation, solving linear equations, I'm sorry. In this linear equation, you see here, this linear equation can be written in matrix form. And then you can solve this. this linear equation can be written in matrix form like this, and then you can solve for this matrix by solve for x, y, z by various methods that we'll discuss soon. There'll be so many methods. See, we can do hand calculation if it was two unknowns. Simple hand calculation we can do. Just for three unknowns x, y, and z, the calculation becomes tedious. Then what to speak of if there are 10 unknowns to deal with in a linear equation? Whereas, uh, by matrix methods, we can solve very, very easily. All right. And I was using those who are in electrical, electronics, and civil and mechanical. You may have heard of finite element softwares. Okay. ANSYS, Abacus. You must have heard about these softwares, NISA, Nastran, and some of you must be working on it for your final year projects and so on. Now, these are finite element softwares. The background of solving is your matrix methods. When I was doing my master's, that was between 98 and 99. When I was doing my master's, I was using Abacus and ANSYS. That time, the maximum size that these softwares could handle, a matrix size, was 99,000 by 99,000. All right. After that, it was like, oh, you have to simplify your way you give your input. Otherwise, 99,000 by 99,000. This was the size. But now it is unlimited. Now with the computing facilities, we have unlimited. So the basic matrix methods that you are doing now, you will have to use them at a higher level of study. All right. If you are going to deal with finite element modules, or uh, flexibility or displacement methods of analysis, and for see, whenever you have a differential equation, you can convert it this way and solve. In my masters, my whole masters project was to do matrix solving only, and I had to write code. I had to prepare code, programming, using a programming language. I had to solve a matrix problem only. So what the basics that we study here has tremendous impact in your understanding of engineering. So although one may think, what this matrix is something very simple, but later on you will know how powerful these tools are. Okay, the linear algebra. That's why in all higher engineering mathematics also, linear algebra is discussed. So that was the background. Now we start with the basics, and we build on this subject. So in GATE and IES, the concepts they ask in linear algebra, all right, the concepts that are asked primarily are rank of a matrix, okay, then solution types for linear equations, whether the linear equations have infinite roots or infinite solutions or finite solutions, so on. Very important, they ask for eigenvalues and eigenvectors. All right. These are the three things that prominent. If you take 70 questions or 100 questions, Around 75 questions will be on these, and remaining 25 questions will be on some properties of matrices and determinants. Directly or indirectly. However, the main focus is on these. But to reach here, we have to learn the basics. So, what is a matrix? We know. I'm not going to go by, I'm not going to give you, I'll be giving you notes, like I will share. Those of you have will join fully with me, then I'll be sharing notes like this. All right. And I'll be teaching you based on this, but I'll not be dictating, because I'll focus more on problem solving. I'll not be dictating detailed notes as it may be done in the college level classrooms. So matrix is a rectangular array of numbers following certain rules, right? So it's a rectangular array of numbers. These horizontal lines are called as, yes, please participate. I want students to discuss now, because these are some topics that you've already learned. It is not difficult for you. Yes, anybody wants to share? What are these horizontal rows in a matrix, uh, horizontal lines in a matrix called? Rows. All right. Okay, these are called as rows. All right. And what are these vertical lines called?
Columns, sir.
Columns. So these are called as columns. So this is column 1, column 2, column 3, column 4. So this matrix is of order 2 by 4 or 2 cross 4. 2 stands for rows and 4 for columns. So a matrix, so general notation of a matrix is we write Aij m cross n. All right. M is the number of rows. So I stand for the number of rows. So I will vary from 1, 2 up to m, and J will vary from 1 to n. So this is a matrix of order m by n, or m cross n. Okay. So this is the general notation of the matrix. So when we expand this, this is like A11, A12, A13, A1, N, A21, A22, A23, A2N, A M1, AM2, AM3, AMN. So this is a matrix where in Aij, I represents notation for the row and J represents the notation for the column. So you see here, in this row, all the elements have the first subscript as 1, meaning that it is row 1. In the second row, the first of the two subscripts ij, so I represents the row. So all the elements have the first subscript as 2, so on, and the last row has all the first subscripts of the elements as m. Okay, so these are m rows and then n columns. So column, you see the second subscript, this represents column 1. The second subscript here for column 2 is 2. The second subscript for column 3 is 3. And for the last column, the second subscript is n. Okay, it's m and n. So a, I, j. I and j are the two subscripts for this notation. So that is a matrix. Now there is a classification of matrix based on, there are two classifications actually. Yeah, types of matrices. I say now based on its structure. Based on the structure of the matrix and the content of the elements, you have a certain type. And there is types of matrices based on properties. Now we'll come to that one by one. The first one is a row matrix. What is a row matrix? What is a row matrix? Anybody? Please share. Please feel free. Don't feel shy. You know the answers. What do you mean by a row matrix? You can, if you are shy to answer, you chat.
There are only rows and no columns are present in the matrices.
Yes, that means there is only one row. Row matrix means there is only one row. Okay, one row. So you have A, 1j. The order of the matrix will be 1 cross n. This is a row matrix. Okay. Example, you can say A is a matrix which has 1, 5, 11. This is a row, one row and 3 columns, but it is called as a row matrix. Second is column matrix. What is a column matrix? Again, answer. If you can answer row matrix, then what is column matrix?
It has only and rows are present in.
Yeah. So it has only one column. So it is m cross 1. It has only one column. All right. So this is a column matrix. Example of column matrix. We deal with lot of column matrix in engineering, especially we solve simultaneous equations. We deal with column matrices. The variable matrix usually is a column matrix. Okay. Then row matrix, column matrix, then we have a rectangular matrix. The notation, see the notation, the way I'm writing. A is Aij, where, oh, okay, Aij order m by n, where m is not equal to n. The number of rows is not equal to number of columns. That is a rectangular matrix. In engineering problem solving and numerical methods, we sometimes have to deal with rectangular matrices. So let us say 2, 4, 6, 8, and 1, 5, 9, 13. This is a rectangular matrix. 2 rows, 4 columns, or 1, 0, 0, 1, 2, 1, 1, 2. These are 4 rows and 2 columns. It can be 3 by 4 or 4 by 3. So many combinations are possible. This is a rectangular matrix. The most important of all matrices is square matrix. And our notation for square matrix is M is equal to N. The number of rows is equal to the number of columns. The number of rows is equal to the number of columns. So this is a square matrix. So there's a square matrix of third order. Okay, order for square matrix, we just say order 3 or order n, means it is n by n matrix. It is understood when you say square matrix of order 3, it is 3 by 3 matrix. Okay, next, diagonal matrix. What's a diagonal matrix?
There are all elements of the matrix directly.
Okay, how will you represent by a small notation? Diagonal matrix is a square matrix, by the way. I will write it as n by n. Diagonal matrix is a square matrix. Okay, it is a square matrix where Aij is not equal to 0, or I would write like this, is not equal to 0 for I not equal to j, sorry, for I equal to j, and it is equal to 0 for I not equal to j. That means, see here, diagonal matrix, the diagonal elements will always be A11, A22, A33, so on. The diagonal matrix will be of this form. So when you write this, A11, A12, A13, A21, A22, A23, A31, A32, A33. The diagonal matrix is these are the diagonal elements. These are this is called as the principal diagonal. There are 2 diagonals, but this diagonal is called as the principal diagonal, and this is of importance, not the other diagonal. So your principal diagonal terms will not be equal to 0. At least not all of them will be equal to 0. So you have 2, 1, 2, and rest of the elements will be 0. So this is a diagonal matrix. So diagonal elements, principal diagonal elements are not zero. So Aij is not equal to 0 for I equal to j, and Aij is equal to 0 for I not equal to j. So these entities will be 0. So, okay, the lower triangular elements and the upper triangular elements here, these will be 0. That's a diagonal matrix. Then scalar matrix. This is diagonal matrix with scalar matrix.
So one question here.
Yes.
So you're considering the diagonal means the one diagonals, and we can see like we have two diagonals.
Yes.
If we try to plot, so why we are not taking the other one? Is there any reason?
Because actually in our solution of linear equations, these principal diagonal terms will be the most critical. Okay, just let us go back to this equation here. See, we have converted this linear equation in the matrix form. Okay, so these are the diagonal elements a1, b2, c3. These are the diagonal elements. Now these play a very prominent role in your solution of equations. So generally what we do is like this: when you try to solve an equation, what do? We try to keep this term as it is and make the coefficients of y and z 0, so that you will find x. Then for the second equation, we try to adjust in such a way that other than this term, we make the other elements 0. Other two coefficients zeros. This is Gauss-Jordan method that we do. Actually, we do by hand calculation the same thing. Gauss-Jordan method is the matrix approach. So the principal diagonal elements play a very prominent role, not the other secondary diagonal elements. Okay, in solution of linear equations. So they are of very special significance compared to the other diagonal. So other diagonal, when they multiply, you can relate a1 straight away to x, b1 to y, and c3 to z. If these other terms, other elements are made 0, directly you will get this. So the whole idea of Gauss-Jordan method is you convert this matrix in such a way that you get here 1, 1, 1, 0, 0, 0, 0, 0, 0, and multiply with x, y, z, and you will get the solution here. Whatever is the solution. That means x is equal to a, y equal to b, z equal to c. Did you understand?
Okay.
Because the way we describe or way we define the matrix multiplication, that makes this principal diagonal terms to be prominent. It's a good question, fundamental question. Now, scalar matrix. So scalar matrix is it's a diagonal matrix where, tell me, what is a scalar matrix? Does anybody know? It's a diagonal matrix.
Diagonal elements equal to 1.
Very good. So off diagonal elements are 0 and the principal diagonal elements are 1. There's a scalar matrix. This is um, in fact, for a scalar matrix, there's a difference between a unit matrix and a scalar matrix. For scalar matrix, it will be equal to some constant k. All right. For example, 3, 3, 3, it's a scalar matrix. Why is it called a scalar? Why is it called a scalar? You see this. Suppose you multiply it this with the column matrix. What we get is 3x, 3y, 3z upon multiplication. It is 3 times. It is as if you multiply this column matrix with a constant, a scalar real number. That is why it is called as a scalar matrix. Off diagonal elements is a constant. Now, unit matrix or identity matrix is a scalar matrix with the value of k as 1. So we know this. This is from high school. We have studied this, that unit matrix are matrices with diagonal elements 1 and off diagonal elements 0. Because you multiply this with any of the matrix, you will get the matrix itself. Just like in real numbers, you multiply 1 with any number, you get the number itself. Like that, in matrices, you multiply the unit matrix with any of the other matrix. Of course, they have to be conformal, that we'll discuss for matrix multiplication. So that's why this is called as a unit matrix. All right. This is unit matrix or identity matrix. Then we have null matrix. This is easy to understand. It need not be a square matrix. All elements are zeros. It need not be a square matrix. It can also be a square matrix, but it need not be a square matrix. So this is null matrix. All right. Then what next? Then you have, yeah, this is in matrix algebra. These two are extremely important matrices. Upper triangular matrix and lower triangular matrix. Does anybody know what these two matrices are? What is a upper triangular matrix?
The element will be the lower part of the matrix plus 3.
Voice is not clear. Voice is not clear. Can you try it again?
Is it clear, sir?
No, there is so much noise.
Maybe I'll type it.
Okay. So in the upper triangular matrix, what happens is the elements below the principal diagonal are zeros. Okay, elements below the diagonal. When we say diagonal, it is the principal diagonal only. So basically Aij is 0 whenever I is greater than j. Whenever I is greater than j, it will be 0. So here you see A11, A12, A13, A21, A22, A23, A31, A32, A33. I is greater than j. So I is greater than j in these cases. 21, 31, 32. So these elements are zeros. So you get a matrix like this. This type of matrix is called as an upper triangular matrix. Why? You see here the elements that are not zero form a triangle on the upper side of the matrix. So this is called as the upper triangular matrix. All right. This is very, very useful in Gauss elimination method of solving simultaneous equations. Lower triangular matrix. This is not so much used as the upper triangular matrix. If we can define upper triangular matrix, lower triangular matrix is easy. What is it? How will you
Elements
define?
above the diagonal are
Yes, elements above the diagonal are zero. Good.
elements above the diagonal.
Yes. So we write like this: Aij is equal to 0 for all or for every I less than j. All right. So elements above the diagonal, the principal diagonal, are 0. Elements above the principal diagonal are 0. This is the upper triangular matrix. So again, the same here. I will repeat this. So now I less than j happens for these elements. I is the first subscript, j is the second subscript. I is less than j for this. So
Sir, I think the 0 should be above.
pardon? Yeah. So here these should be 0 and so elements above the diagonal are 0 whereas others are not. So now when you see the elements below the diagonal and below the diagonal, they form a triangle. Of course, one important thing about lower triangular matrix and upper triangular matrix is one of the elements or two of the elements can be zeros. It is not that they need not be. But elements below the principal diagonal must be 0, all of them. So this also an upper triangular matrix here. Just because it is 0 here, that is not that it is not an upper triangular matrix. Similarly, here you can have a 0. However, elements above the upper diagonal, the principal diagonal must be 0. Okay, so that's the idea. Okay, now there are operations on matrices, and then properties of matrices based on those. So algebra of matrices, or the matrix algebra, basically. So first one is the addition. Okay, we are now, when we say matrices, there are two matrices. So equality of matrices, and then we'll go for addition. Equality of matrices, when are two matrices A and B said to be equal? Anybody? A and B are two matrices. Okay, when are they said to be equal?
When determinants are same, I think.
No, no. When are two matrices said to be equal?
When Aij equals Bij.
Okay, and
When its
the
order
Aij,
and elements are equal.
yes, very good, very good.
Same.
Orders of A and B must be equal. For first step. Then first this condition must be satisfied. Second condition is Aij will be equal to Bij for all I comma j. This notation is for all. Okay, for all, for every. All right, so when I write these notations, so Aij is equal to Bij for all I and j. Okay, this is the equality of matrix. So yeah, Amit, I'm muting you because of this noise. Yeah, now just look at this. This is 2 1 2 0 3 0. This is 2 1 2 0 3 0. Elements are the same, but the matrices are not equal, because the orders are different. All right, example 2, the orders are different. Example 2, orders are same, elements are different. Okay, now it does not matter if you know A22 and B22 are equal, like these two are same. Every element must be equal. Every element must be equal. Two matrices are said to be equal only when they are of the same order and the same elements. So A, if it is 2 1 0 5, B also has to be okay. If B is X Y Z W, This implies x equal to 2, y equal to 1, z equal to 0, and w equal to 5. So this is about equality of matrices. Okay. Next is the operation of addition of matrices, or the matrix addition. When can two matrices be added? Answer. When can two matrices be added?
Same order.
Yes, very, very good. So matrix um, A and B are conformable for addition. We write like this. A and B are conformable for addition if their orders are same. Only then you can add. So see, matrix A and B will give rise to matrix C, provided the A and B matrices are of the same order. So the notations we are writing like this. We are writing notations like this. Now, when you see here, Cij is equal to Aij plus Bij. I am purposely making this notation form of matrices. There's a reason for it, because you have to get used to it, because in logic and some reasoning questions, these kinds of things are important. And of course, when you write programming, you have to be very clear of these i's and j's in arrays. So for every I and j, okay, Cij is equal to Aij plus Bij. So let us say there are two matrices. Matrix A is 2, 0, 4, 1, and matrix B is 3, 1, minus 2, minus 4. So when you add them, each element, the corresponding elements get added. 2 plus 3 is 5, 0 plus 1 is 1, 4 minus 2 is 2, 1 minus 4 is minus 3. So these corresponding elements get added. All right. That is matrix addition, which we know. It is not a new thing for us. Now, these have properties. Yeah, these questions are important. Whenever you get properties, sometimes suddenly a simple but a tricky question is asked on properties, especially transpose and inverse and so on. So matrix addition is commutative. Means what? Means what? A plus B is equal to B plus A. Okay. It is associative. Means if you have three matrices A, B, C, you can first add A and B and then add C, or you can first add B and C and then add A. They will be the same. They'll be equal, associative. Then additive identity. What is the identity of additive identity? A plus null matrix so null matrix is the identity matrix. So null matrix is the additive identity. All right. Then inverse, additive inverse. What is the additive inverse of A? Anybody? What is an additive inverse of a matrix? No one?
Changing the sign of a particular number.
All right. If to a matrix you add another matrix such that you get a null matrix, all right, that means first of all B and A should be of the same order. Okay, then B is called the additive inverse of A. So B is nothing but minus of A. Multiply every element of A with a negative sign. Okay, and then of course the cancellation laws hold true. Cancellation laws, if A plus B is equal to A plus C, this implies B equal to C. So we can just cancel off A, and suppose we have here, okay, A plus C is equal to B plus C. This is left cancellation law, the first one. The second one is the right cancellation law. Okay, so this is about additions, addition of matrices, how matrices are added. So this is just a review what we have done. There'll be simple questions on that. I'll give you some examples once we finish multiplication. Then multiplication, this is addition of matrices, equality of matrix over, then addition of matrix, then multiplication of matrix. Okay, the whole reason multiplication is defined the way it is defined is to accommodate for the simultaneous equations, that which we discussed in the right in the beginning of the class. All right, this one, the simultaneous equations, so that we are able to write the equations in this form. and then we solve. For that reason, multiplication of matrices is defined like this. The whole idea of developing matrix algebra is to solve simultaneous equations. So if very important, if A is m cross n or m cross p, and matrix A, and B, matrix B, is of the order p cross n, then we define A into B. Okay, A m cross, I will write like this. That this will be equal to C m cross n. So remember, in matrix multiplication, the left matrix is m cross p, the right is p cross n, and you omit the common. Omit the common. That means the rows and the columns. Then m cross n will be the order of the product. Order of the product. Okay. Now A and B are said to be conformable for multiplication if, tell me in words, tell me in words, when can two matrices A and B be multiplied? Anyone?
If m is equal to n.
No.
When the columns of the first matrix equal the rows of the second matrix.
Yes. If the columns of A, the number of columns, actually just the number of columns, if the number of the columns of A is equal to the number of the rows of B. That too for A into B, not for B into A. This is for A into B. Okay, this is conformability of multiplication. So here is the trick actually. So this is so simple. We'll take a simple example. 2, 4, 1, 5 multiplied by 3, 0, 2, 1, let us say. So this is A, this is B. So what we do, row multiplied with the columns. So the answer will be the first row elements get multiplied with the first column elements to give the first row, first column element of the product. So 2 into 3 plus 4 into 2. 2 into 3 plus 4 into 2. The first row, second column and column element of the product will be 2 into 0 plus 4 into 1. 2 into 0 plus 4 into 1. Then the second row, first column element, 1 into 3 plus 5 into 2. And then the last row, last column element, 1 into 5, sorry, 1, 5 multiplied with 0 and 1. So 1 into 0 plus 5 into 1. So the product is 6 plus 8, 14, 4, 13, 5. So this is how matrix multiplication is defined. Okay. Now, properties of multiplication. Here, likely questions. Okay, first addition was commutative. Property multiplication is not commutative. Okay, AB is not equal to BA. Many times BA may not exist. All right, BA may not even be defined. If they are not square matrices, then AB, BA may not be defined also. Okay, so in fact, we do the other way around. We do this multiplication here. Just now we did AB, now we do BA. 3021 multiplied with 2415. The product is 3 into 2, 6 plus 0, 6. 3 into 4, 12 plus 0, 12. And 2 into 2, 4 plus 1 into 1, 5. 2 into 4, 8 plus 5, 13. This is 6, 12, 5, 13. This is 14, 4, 13, 5. So AB is not equal to BA, even though they exist. Even if they exist, they are not equal. Okay. So this is the commutative property of matrices, non-commutative property. Then associative, as long as conformability exists, associative property holds. Matrix multiplication exists as long as they are conformable. That is, A times BC will be equal to AB times C. Okay, this is valid as long as conformability for multiplication exists. Okay. Next. Now matrix multiplication is distributive over addition. So A multiplied by B plus C is AB plus AC. See the sequence. If I do B plus C times A, it will be BA plus CA. Okay, this is distributive. Multiplication is distributive over addition. Then identity matrix. A into I is I into A is equal to A. Okay, if A is n by n, all right, not necessarily, but suppose it is 1 0 0 1. So, but generally this is valid for a square matrix, but you can have identity matrix with rectangular matrix also. Okay, suppose A is m cross n, let us say, then I has to be n cross n, and this I has to be m cross m. Then in this case this will be m cross m matrix. Did we understand? So identity matrix I is 1 0 0 1 or 1 1 1 m times and rest all zeros. So identity. Then inverse. Then inverse of a matrix. Of course, this is a big topic. We have to discuss singularity. Okay, if there exists such that if AB is equal to BA is equal to I, it is of a square matrix. Then B is called as the inverse of A. For that, there are certain rules to follow. Singularity condition, non-singularity condition, I'm sorry. So we'll discuss all that. Next. Okay, tell me this. If A into B is equal to 0, then what does it mean? Then what does it mean? If A equal to A into B equal to 0.
Any matrix should be null matrix.
All right, then. Okay, very important. It is not necessary that any one of them is null matrix. We will take an example. Say 2 2 1 0 0 2 1, okay, 2 0 0 1 0 0 5 4. None of these are null matrices, but when you do A into B, you see what happens. 2 into 0 plus 0 into 5 0, 2 into 0 plus 0 into 4 0, 1 into 0 0 into 5 0, 1 into 0 0 into 4 0. However, BA may not give you that. The 0 0 multiplied by 2 and 1, you get 0. 0, 0 multiplied by 0, 0, you get 0. Then 5, 4 multiplied by 2 and 1. 5 into 2, 10 plus 1 into 4, 14, 0. So BA is not equal to 0, but AB is 0. Neither A is 0 nor B is 0. Okay. So you have to be thoughtful. So you may get a tricky question, a simple question on matrix understanding like this. So these are properties of multiplication. So equality we have discussed, addition we have discussed. Very important operation on matrix is transpose. Okay. So if A is an m by n matrix, then A transpose is defined as AJI n by m. That means A transpose is a matrix whose rows and columns are interchanged in the original matrix A. So this is 2 minus 1 3 0 0 3 5 or 0 4 6, let us say. This is A. Then what is A transpose? The first row becomes the first column. 2 minus 1 3, and then the second row becomes the second column. 0 4 6. Okay. So row and columns get interchanged. So there's a transpose of a matrix. And then there are properties of transpose. What are properties of transpose? A transpose holds transpose is equal to A. Now these are important properties, and again in various methods of solution of simultaneous equations. Now A plus B the whole transpose is A transpose plus B transpose. This is important. AB the whole transpose is equal to B transpose A transpose. And suppose we multiply with a scalar. K is a scalar. Then it is K times A transpose. All right. So these are properties. One important thing about scalar multiplication, which I missed here in properties of multiplication, I should have written here. See, K times a matrix A is same as you multiply every of its element with that k. That is the scalar multiplication. This we know. That means if 2 into 1, 3, 5, 7 will be equal to 2, 6, 10, 14. Every element will be multiplied. That is the scalar multiplication. So today, what we discussed is very basics of matrices. We discussed the basic definitions, the basic definition, the types of matrices based on the structure. We discussed 3 properties: addition, multiplication, and transpose. Okay. We have adjoint. Before that, we'll have to discuss in the next session. Before we discuss further, before we come to linear equations, we have to discuss determinants. This is the next session. Determinants, then adjoint. Adjoint of a matrix we'll discuss with determinants only, and inverse. Then we discuss rank of a matrix. After we discuss these, then we are prepared for entering into our main topic, that is simultaneous equations. So this will take considerable time, at least 1 hour, and the rank may take, and then we'll get into simultaneous equations.